Welcome back to The Explainer. Today, we're diving into something kind of mind-blowing. We're unlocking the invisible engine that powers modern materials science. It's a phenomenon that dictates literally everything, from how strong the gears in your car are to the processing power of the smartphone sitting in your pocket right now. I'm absolutely thrilled to guide you through this because I promise you, once you understand what's happening down at the atomic level, you're never going to look at a piece of metal the same way again. Think about a solid steel beam, or maybe a block of aluminum. Intuition tells us that these objects are, perfectly static, right? They're solid, hard, and seemingly frozen in place. But I want to challenge that assumption right out of the gate. Down at the microscopic level, these solid objects are actually buzzing with hidden movement. So the big question we're tackling today is, how do atoms actually move through a solid metal? Okay, let's dive into this. The official term for this movement is diffusion. Simply put, diffusion is mass transport by atomic motion. It's the step-by-step migration of atoms from one spot in a material's crystal lattice to another. Now, in gases and liquids, molecules just bounce around randomly, what we call Brownian motion. But in solids, the atoms are locked into a grid. For them to move, they need specific mechanisms. It's like a giant puzzle. Here's our roadmap for today. We're going to quickly cover 1. The basics of diffusion. 2. How atoms actually move. 3. Diffusion in industry. 4. Fick's first law. 5. Fick's second law. And finally, 6. The temperature factor. Let's jump right in. Section 1. The basics of diffusion. Intradiffusion versus self-diffusion. So, the golden rule of diffusion is that atoms naturally tend to migrate from regions of high concentration to regions of low concentration. Think of dropping some ink into a glass of water and watching it slowly spread out. Well, in solid materials, this behavior takes two main forms. First up, there is interdiffusion. This is when atoms of one material diffuse into a completely different material. You've got this concentration gradient where the foreign atoms spread out until they're totally evenly distributed. On the flip side, we have self-diffusion. Even in a completely pure piece of metal, let's say a chunk of pure copper, the host atoms are constantly migrating and swapping places with each other. We just can't easily see it happening because, well, all the atoms look exactly the same. Moving right along to Section 2. How atoms actually move. The microscopic mechanisms. Down at the atomic level, atoms basically have two primary ways to get around inside a solid crystal lattice. Over on the left, we've got vacancy diffusion. Atoms and vacancies, which are just empty, missing spots in the lattice, exchange positions. I always like to think of this as a sliding tile puzzle. You can only move a tile if there's an empty square right next to it, right? The speed of this diffusion really depends on how many of those vacancies exist and the energy it takes to make the jump. Now on the right, we have interstitial diffusion. This is where smaller impurity atoms just squeeze right into the empty spaces, or interstices, between the larger host atoms. Because these little guys are tiny, they don't have to wait for a vacancy to open up. It's kind of like a small person weaving quickly through a super crowded room. Because of that, interstitial diffusion is much, much faster than vacancy diffusion. Section 3. Diffusion in industry. Building better materials. Now, this is where theory meets reality. Think about this mechanical gear right here. In high-stress environments, gears need an incredibly hard exterior so they don't wear down, but they also need a tough, flexible interior so they don't just shatter under impact. So how do engineers pull that off? Through a process called case hardening. By placing a solid steel gear in a carbon-rich environment at really high temperatures, those tiny carbon atoms undergo interstitial diffusion right into the outer surface of the steel. Because those carbon atoms are forcefully squeezing between the iron atoms, they create massive residual compressive stresses. This hardened case locks the surface tight, which is an absolute game changer for improving wear resistance and preventing fatigue failure. And this brilliantly illustrates another massive industrial application: semiconductors. The microchips running basically our entire world rely on silicon, but pure silicon actually isn't a great conductor on its own. To make it work, we use a process called doping. We deposit a phosphorus-rich layer right on the surface of the silicon, then we heat treat it. That thermal energy drives the tiny phosphorus atoms to diffuse right into the silicon lattice. It is absolutely wild, but just a microscopic amount of diffused impurities completely rewires the electrical properties of the material. It turns ordinary silicon into the highly precise p-type and n-type regions that form the literal foundation of modern electronics. Which brings us to Section 4. Fick's first law, the maths of steady state. Now, please don't let the equations intimidate you here. This is just narrative math describing exactly what we've already been talking about. Fick's first law describes steady state diffusion. That simply means the rate of diffusion isn't changing over time. It's constant. The equation states that J equals negative d times dc over dx. Let's break that down real quick. J is the diffusion flux, basically the mass of atoms passing through a specific area over a given time. D is the diffusion coefficient. Think of D as a measure of how easily atoms can move through a specific material. And dc over dx is the concentration gradient. The steeper that gradient is, meaning a super high concentration on one side and a super low concentration on the other, the faster the atoms will flow. It's honestly just like water flowing down a hill. A steeper hill means faster water. Let's see how this actually plays out in a real-world safety scenario. Imagine you're working with a harsh paint remover containing methylene chloride. Now, this stuff can absorb right through your skin. So you might wonder, can I just use standard 0.04 centimeter thick butyl rubber kitchen gloves to protect myself? Well, by plugging our values into Fick's first law, using the known concentration of the chemical on the outside, the desired zero concentration on the inside, the exact glove thickness, and the diffusion coefficient of rubber, we can actually calculate the flux, J. The math reveals that the flux is 1.16 times 10 to the negative 5. To put that into perspective, the absolute maximum allowable safe flux for a human is significantly lower than that. The equation explicitly proves that those flimsy kitchen gloves would let 30 times the safe limit of toxic chemicals diffuse right through the solid rubber onto your skin. Definitely not a good idea. All right, Section 5, Fick's second law, non-steady state diffusion. So the crucial point here is distinguishing between these two states. Fick's first law only works when the diffusion rate is perfectly constant, totally independent of time. But in the real world, like when we are case hardening that steel gear or doping that silicon chip, the concentration of the diffusing atoms is constantly changing as they pack into the material. The concentration is a function of both how deep into the material you're looking and how long the process has been running. Obviously, this requires a slightly more dynamic equation. Enter Fick's second law. Now, this partial differential equation, where the change in concentration over time equals the diffusion coefficient times the second derivative of concentration with respect to position, okay, it looks a bit intense, sure, but its purpose is incredibly practical. It allows engineers to predict the exact concentration of a diffusing element at a specific depth inside a material at a specific moment in time. Think about it. If you need a gear hardened to exactly 2 millimeters deep, Fick's second law is exactly what tells you how many hours you need to leave it in the furnace. Finally, Section 6, the temperature factor, pushing the limits. So what's the biggest control knob we have over all of this? Heat. The relationship between temperature and that diffusion coefficient D is defined by the Arrhenius equation. Atoms need a specific amount of energy just to break their bonds and squeeze into a new position. We call this the activation energy, or QD. As the absolute temperature T goes up, the thermal energy of the atoms absolutely skyrockets. And because that temperature variable sits in the denominator of a negative exponent in this equation, even a tiny little increase in heat causes a massive, exponential increase in the rate of diffusion. Basically, temperature dictates the absolute willingness of these atoms to move. Now, what's really interesting about this slide is how vividly it demonstrates everything we've just learned. Notice how dramatically these lines slope upward on the graph? That is the sheer exponential power of temperature at work. But look a little closer at the different lines. The blue and purple lines represent carbon diffusing into iron. That's our interstitial mechanism, where the tiny carbon atoms just weave through the open spaces. But the red lines, they represent iron diffusing into iron, or aluminum into aluminum. That's the vacancy mechanism, our slow sliding tile puzzle. Across every single temperature point on this chart, the lines for interstitial diffusion are sitting way, way higher up. It visually proves that interstitial diffusion is orders of magnitude faster than substitutional vacancy diffusion. No contest. We've journeyed all the way from understanding how an empty vacancy allows a single atom to slide over, all the way to predicting the exact time and temperature an engineer needs to harden an industrial gear. But as we push our engineering into deeper space, higher pressures, and hotter reactors, I want to leave you with this thought. By manipulating these exact laws of diffusion, how might future materials be designed to either entirely resist or purposefully accelerate atomic migration under the most extreme conditions imaginable? The math and physics we explored today are really just the starting tools for whoever answers that question next. Thanks so much for joining me on this explainer, and keep exploring.